Let's dim an LED. Actually, you can't dim an LED. An LED is a binary device, 1 or 0. It's either on or off. Okay, Tarnoff, you're messing with me now because I have clearly seen an LED dim. When my computer is in sleep mode, I see the LED kind of slowly dim down and then brighten and then slowly dim down and then brighten. No, you're not seeing it dim down. What you're seeing is, well, let me show you. My lighting, part of my lighting here, I've got some LEDs, all right? And I'm going to take let's set them on full intensity. And then I'm going to just do a quick video, actually a slow motion video, to show you what's happening. And now let's turn them down and take another video. See the blinking? Yeah, it's blinking. Doesn't look like it's blinking, but that's because your eyes do not see the blinking because it's blinking too fast. It's blinking faster than your eye can sense. The permanence, whatever, that vision thing that makes it so that we can kind of take frames, whether it's video or whatever it is, even fluorescent lights or even these LEDs, and it actually kind of smooths it out so that it looks like it's a continuous video. It turns out that these things are blinking. And they're blinking with that thing that we talked about last time, a periodic pulse train. Now, if you look at this periodic pulse train, you'll see that this particular one, and remember what we've got is this time between either consecutive falling edges or consecutive rising edges, which we referred to as T for a period. That was the period, remember? And it was measured in seconds. Specifically seconds per cycle, but seconds, right? And then we also had that other measurement which measured the width of a pulse, a positive going pulse. That was T sub W. T sub W is also measured in seconds, all right? Now, if I were to ask you, just kind of looking at that signal right there, would you consider that, what percentage of time would you consider that to be a logic 1? Well, it kind of looks like about 50%, all right? Well, this brings us to a term called duty cycle. Now, a duty cycle is basically the percent of time a periodic pulse train equals 1, a logic 1, all right? Now, another way of looking at it, and engineers will often look at this as how much power, what percentage of the total possible power are we sending to this output? And in this case, we're a logic 1 50% of the time, so we're sending about 50% of the power. So we would say that the duty cycle for this guy is 50%. All right. Now, if we wanted to have the LEDs on full, you know, as the 100% power, well, that's actually just a constant. Whoop, I need to have a little bit better pen here, don't I? That is going to be a constant logic 1. And this is a duty cycle of 100%. Right? What about if we want to turn the LEDs off? Well, if we have a constant logic 0, see if I can get technology to help me out here a little bit here. There we go. A constant logic 0. Guess what that is? That's a duty cycle of 0%. All right. Now, in between, you know, the pulses as they're coming, as they're getting wider and wider and wider and wider, your duty cycle is slowly but surely increasing. Now, what we've got is this seems like a mathematical thing, right? We can actually come up with some sort of a mathematical expression in order to show what duty cycle is equal to. And I'm going to make a mess of my board here for just a moment. All right. Duty cycle. It is equal to, and it's a ratio. Remember, it's a percentage of time that the signal is a logic 1. So T sub W, remember, that is the time we're a logic 1. Capital T, that is a full period. So T sub W over capital T, that says that is going to give us a fraction. To convert that to percentage, we need to multiply that by 100%. All right. And this is the expression, very simple mathematical expression. So if I were to look at this expression and say, okay, T is equal to, I don't know, a second. Let's say that it's a 1 hertz signal. T is equal to 1 second. T sub W is equal to 0.5 seconds. Then 0.5 over T would give us 0.5. If 0.5 over 1 give us 0.5 times 100 would give us 50%. That brings us to something though. Let's just do a really quick example here. I've got some sort of a periodic pulse train here. And I am going to say that, I don't know, the period, let's say that the period is equal to, I don't know, how about 250 microseconds. A microsecond is 10 to the negative 6th seconds. And let's look at the pulse width, capital T sub W. The pulse width, I don't know, let's just say it's 50 microseconds. All right, so 50 microseconds, that's the amount of time we've got a logic 1 over a period of 250 microseconds. That means that our duty cycle is equal to 50 microseconds over 250 microseconds. Now, there's something very important to see here. Actually, I forgot, I guess my times 100%, didn't I? Now, there's something very important to see here. The microseconds cancel out. And by having the microseconds cancel out, what ends up happening is we've just got a unitless, well, it's got units of percent, sort of. Percent is not really a unit, but it's a unitless measurement. Duty cycle is a unitless measurement. So what we've got is basically 1/5, which is equal to what, 0.2 times 100%. So this means we've got a 20% duty cycle. That means that this signal right here is a logic 1 20% of the time. Now, guess what? This would work the same if this period were 5 seconds and the pulse width was 1 second. So for 5 seconds, we have 5 seconds between pulses, or between rising edges of the pulses, and each pulse is only 1 second long. Guess what? It has exactly the same duty cycle. So duty cycle cannot be used to determine frequency. Frequency is it completely drops out, as does the period. But this gives us the ability to compute duty cycle. Now, what does this have to do with LEDs? Well, it turns out that a lot of for example, these embedded systems like Arduino, maybe many of you have heard of an Arduino. They have functions, they have routines that you can call that can give the duty cycle to one of their digital outputs. If that digital output is driving an LED, guess what? You can dim an LED.